Welcome learners in the series of videos on topology. In the previous videos, we have talked about countability properties. That is, first countable space, second countable space, separation, separable spaces and all. Okay. Now let's start with another series where we will talk about separation properties. Okay. So let me first write it. Separation properties. Okay. Now, if you remember, we have already talked about T1 space. Okay. We have taken the definition of T1 space. We have also seen what are T2 spaces. Okay. These T2 spaces are called Hausdorff space. We have defined this. We have used this. We have taken the examples of these T2 spaces, T1 spaces, and so on. Okay. Now in this series of videos we will talk about these separation properties. Okay, not only T1 T2, we have another properties, another examples, another species. Those are called T0. Then we have T1, which is also called as Seperation. T2 is called Hausdorff. Then this T2 and half, that is Eurozone. Then completely T2 space, completely Hausdorff space, regular Hausdorff space. Then when we have 3 and a half, it is Technop space, T4 and so on. Okay, so we'll talk about this T1. We already seen about T1. Then Hausdorff spaces also we have seen. Now we will see what are T3, that is regular spaces, and T4, what are normal spaces, and some properties related to it. Okay, so let's first define what are the spaces, what are the definitions of these spaces. So let us take first one. Let us take T1 space. Okay, let us take T1 space. T1. So in this video, we will talk just about the definitions of these spaces. Okay, when we call this as a T1 space or not. Okay, so let us take a topological space. A topological space. A topological space. The X is said to be T1, said to be T1 if this happens. If you take for all x and y belonging to the space x not equals to y, so you take two distinct elements from x, any two distinct elements from x, there exist neighborhoods. Say u suffix x, this is the neighborhood of x, and v suffix y, neighborhood of y. So neighborhoods ux and vy of x and y respectively, such that x will not be an element of vy and y will not be an element of ux. Understand this, here we are not saying they are disjoint. Okay, there will be some intersection. Let me just draw a diagram for you. So if we have this space x, suppose we have this x, right? Now in this x, if we take any two elements, say x and y, suppose we have taken x and we have taken y, what it says, for any x and y which are distinct, there should exist the neighborhoods of x and y such that y will not be an element of the neighborhood of x and x will not be an element of neighborhood of y. So those neighborhoods, let me just it like this. So this says ux and say this is vy. So they may have intersection, ux intersection vy may be non-empty, they may have some intersection, but the guarantee should be like this x should not be in vy and this y should not be in ux. Okay, this should happen for all the points x and y in x, then we say a space is T1 space. Okay, this is about T1 space. Let's go for T2 space. Second one, let me write Hausdorff space. Hausdorff space. That's also denoted by T2. Again, same. Here we wanted the neighborhoods of this x and y such that x is not in Vy and y is not in Ux. But if we can find the neighborhoods such that their intersection is empty, it means they are disjoint neighborhoods, then the space is called Hausdorff space. So the definition is, for all x, y belonging to x, x not equals to y, there exist ux and vy, neighborhoods of x and y respectively, such that ux intersection vy is empty, no matter what point we are taking. Okay, so let us write that definition. We have already taken this, we have already seen the examples of Hausdorff spaces. Okay, a topological space the x is said to be T2, or that is also called as Hausdorff, if you take any elements x and y, so for all x and y in X, those are distinct, say x not equals to y, there exist neighborhoods, those are the open sets, neighborhoods ux and vy of x and y. That means x is a neighborhood of ux is a neighborhood of x and vy is a neighborhood of y respectively, such that ux intersection vy is equals to empty. And if we want to draw the diagram, do like suppose this is our x. Now, if we take any 2 points in x, say x and y, suppose this is x and this is y, no matter where you are taking, no matter how close you are taking, there should exist two open sets, say neighborhood of x, say ux, so this is ux, and another neighborhood, say vy, so this is vy, such that the intersection is empty. Okay, now if you see the definition of T1 and T2 spaces, you can get the relation that whether T1 space is T2 space or all T2 spaces are T1 space. Okay, now here the thing is their intersection is empty, and for T1 space you need not have intersection is empty. Okay, so naturally you can easily prove that a T2 space, that is Hausdorff space, is always T1 space. So T2 implies T1. Okay, so these two spaces we already seen. Let's go ahead and define something called as regular spaces. So let us define third one, regular space. Regular spaces, and these are also called T3 spaces. Okay, so now here a topological space. Let me first write topological space. X is said to be regular, or we also call as T3, if there are 2 points. First, every singleton in X is closed in X. So in previous videos we have talked about this T1 spaces. Okay, so in T1 spaces every singleton is closed. Those things we have already proved, I guess. Okay, and this is the first point. And second point, it says for every closed set closed set, let me write closed subset. For every closed subset, let us take A of X and a point which is not in A. So a point in X difference A. Okay, so you take a closed set and you take a point which is not in the closed set A, then there exist open sets say U and V in X. So U and V are open in X such that this X, let us take A. So A is a subset of U and X belongs to V. So what it means is, for every closed set and for every point which is not in a closed set, there exist two open sets such that A will be inside U and X will be in V, and another point is they should be disjoint. So U intersection V should be empty. Okay, so if you need to draw the diagram of this, it's very simple to understand the diagram. So let us take this as X. Okay, and we have a subset of X. So we have, say, this A is a subset of X, and you take a point outside A. This A, so you take a point X is outside A. So we have some X here. No matter how close you are, doesn't matter. Okay, it says there exist two open sets in X such that one open set will contain A and another open set will contain X. So there exist two open sets. Say, so there exist two open sets. One will contain X and another will contain A. So this is our U and this is our V. Okay. Now if we compare this with Hausdorff space, then what is the relation between regular spaces and Hausdorff spaces? What I meant to say is every regular space a Hausdorff space, or is every Hausdorff space a regular space, or there is no relation? It means there may be some regular space which is not Hausdorff, and there will be some Hausdorff space which is not regular. That relation we can find it out. And another, let us take T4. T4 is just extension of the space T3. Let's go for T4. That is, T4 is also called normal spaces. So normal spaces. So in T3 we need a closed set. We have a closed set and a point. Now for normal spaces we need two closed sets. So it says if you have two closed sets those are disjoint, then there exist two open sets which will contain those two subsets, and the intersection of those open sets is empty. So let me just put that in words. A topological space say X is said to be normal if normal, or is also called as T4. Okay, normal or T4 if, again as in the T3 we have 2 points. First, singleton sets are closed in X. There is also a point in T3, and the second one, as I said, for every pair of closed sets, say A and B of X, which are disjoint, so with A intersection B is equals to empty, Okay, there exist open sets, open sets, say u and v in X. So this u and v are open in X, such that A will be contained inside U, B will be contained inside V, and U intersection V is equals to empty. So they are disjoint. Okay. So let me again, for your information, let us put that in a simple diagram. This is our X full space. We have two subsets. So let us take this in the same color. Say this is our A, which are closed sets, both are closed sets. This is our B. Okay. Now it says there are two disjoint open sets. One will contain A and another will contain B. Okay. So there are two disjoint open sets which contains A and another will contain B. So this is U and this is V. So if such a situation is there, then we say that the space, whatever space, topological space X, we say that it's a normal space, or also it is called T4 space. So the natural question is, what is the relation between these spaces? Is T1 space always T4 space, or is it true that T4 space is T1 space? Okay, so this thing I will do for a learner to understand, to give the examples. So if you say that every T3 space is T4 space, but ulta is not true, that means T4 space is not a T3 space, then you find the example, you find the counter example and validate your statement. Okay, so that one I will leave as exercise. Okay. Now in the next video, we will prove that if you take a matrix space, if you take any matrix space, then it is always normal. Every matrix space is, that will do in the next video. Till then, stay safe.